Hello, and welcome to this Smith's Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters and talk about our agenda. With us today is Kevin DeFord. Kevin is a Defense, Space, and Aerospace Senior Product Commercial Manager. Also with us today is Kyle Gobble. Kyle is a Product Line Manager. So now let's talk about today's agenda. Today we will focus on Smith's KVPX backplane connectors and its newly released space-qualified version. So some of the things we're going to talk about today, we're going to do our introduction to our standard KVPX hyperboloid technology. We'll understand the requirements of EEE INST 002. We're going to be discovering the benefits and features of our KVPX for space. And after all that, we will have our live Q&A session and an open discussion. And with that, I am going to pass things along to Kevin to get this webinar going. So Kevin, go right ahead.
Thank you, Katie. Can you just confirm if you can hear me okay?
Kevin, you sound great. Go right ahead.
All right. Well, thank you, everybody. Thank you for your time today. Good morning, good afternoon, good evening. So let's talk about KVPX. So, slide here. So, Smith's Interconnect KVPX series is an embedded interconnect system that provides unrivaled performance in harsh environments while adapting to the VITA standard design requirements. By utilizing the Hypertech superior hyperboloid contact technology, the KVPX series ensures exceptional tolerance to shock and vibration, has low insertion forces, high current ratings, and the lowest spreading corrosion available. So as discussed in our previous webinar, which dealt with spreading corrosion in contact technologies, our VPX connector has more resistance to spreading corrosion caused by the relative movement of contacts during continual shock and vibration in harsh environments, which is one of the leading causes of failure in aerospace, space, and defense systems. This is especially problematic at the backplane interface of an embedded computer such as avionics, radar, sensors, motor controls, weapon systems, and space applications such as launchers and satellites. To solve the problem, Smith's Interconnect has integrated its legendary Hypertech contact technology into a Beta 46 and 48 form factor by evolving its space-proven compact PCI technology. To that end, the KVPX utilizes a reverse gender versus other backplane connectors, further protecting the metal pins from damage. So KVPX can be designed into standard 3U or 6U configurations. The Beta 46 standard defines the system management architecture for PPX systems. Beta 63 was developed to describe the hyperboloid alternative technology because the backplane connector in our VPX solution is reverse gendered to the connector designed in Beta 46. There are three main connector modules to address differential, single-ended, and power signals, and we will discuss that further in a later slide. The hyperboloid contact system provides 360-degree contact to the mating pin. This is the main feature that provides immunity to shock, vibration, and threading corrosion. The pin in our VPX solution is in the plug-in card, also referred to as the daughter card, which has a faceplate that guards and protects the pins in case of accidental damage. The hyperboloid socket is on the backplane, and they're not intermatable with commercial off-the-shelf solutions. So there are four main components that make up the KVPX backplane system. On the daughter card, you have the right angle connector that has a compliant pin that presses into the PCB and makes a gas-tight seal between the pin and the plated through hole. We will get into the definition of the wafers in a moment, but the connectors are designed to transmit single-ended, or RF, differential, also known as digital, and then DC power signals. The guide socket is also mounted on the daughter card and comes with different keying options. As an optional hyperboloid socket was designed specifically for the guide socket, it can be used to ensure good contact to safety ground. The backplane side also has press-fit compliant pins that press into a plated through hole, creating the physical connection. The half-size connector has 72 hyperboloid sockets, and the full has 144 sockets. The guide pins are mounted to the backplane and have the same complementary keying options to the guide socket. The KVPX guide hardware provides finer alignment than most commercial off-the-shelf guide hardware. The plug-in connector has 4 different wafers that are configured in various ways to make up the KVPX product line. The wafers are configured to make a single-ended differential and power signals in half or 8 in full-width connectors, which have 16 wafers in them. Each connector is coated on the top of the insulator with dashes and dots for identification. So that's, if you look above each of the illustrations, that will show you the mark that's on the top of the connector. So the single-ended connector in the upper left has 5 RF signal lanes and is marked with a dash dot for identification. It has ground traces within the connector and a shield on the left side of the wafer that is common ground. When you stack the wafers together, the wafer to the right, phone call coming in. So when they're stacked together, the wafer on the right side shields the connector to the left, and this is true for all of the configurations. So there's 2 differential wafers, an odd shown in the upper right and an even shown in the lower left. The odd wafer is identified with a dot dash dot and has 2 differential pairs and then 1 single-ended trace. The even wafer has 2 differential pairs and is coated with 2 dots. Upon closer inspection, you can see that the grounds on the odd wafer align to the differential pairs on the even wafer. So this provides better shielding and lowers crosstalk on the daughter card and on the backplane. The 4th wafer type is a power wafer. It's identified with a single dot. Each wafer has 2 power rails capable of carrying 12.5 amps of power with less than 30 degrees temperature rise. Now we'll talk a little bit about the connector configurations. So as mentioned earlier, we have half and full width connectors with 8 and 16 wafers respectively in each. So there are 5 different connector arrangements. Utility, up on the top here, is a half width connector with 3 power wafers, followed by 3 single-ended wafers, and then an odd and an even wafer. In talking about the wafer positions, the first wafer in the connector is always the leftmost wafer. It's important to note that that's when you're looking at the backplane. So as you're looking through the daughter card to the backplane, the leftmost connector is going to be the first connector shown here. So, for example, in the utility, it would be the power. So the next connector that I want to talk about is the full power connector. It has 16 power wafers. So this is a new configuration that was created for a space customer who needed more power. So this connector configuration is currently under test, and the target is to reach 100 amps with less than 30 degrees temperature rise, 30 degrees Celsius temperature rise across all 16 wafers. Excuse me. The full differential has 8 even and 8 odd wafers configured as shown. So the connector can support up to 32 differential signals and 8 single-ended lanes. The next connector has 16 single-ended wafers and can support up to 80 RF signals. So and then finally, another new configuration that was designed specifically for a customer is a hybrid connector. It has 4 odd and 4 even differential wafers and can support 16 differential signals and 44 RF signals. Now we'll talk a little bit about the signal integrity. So insertion loss is the measure of how much signal is lost when passing through a transmission line, in this case our connector. So differential 1 and 3 represent differential lanes on the even wafer, and differential 5 and 7 represent the odd wafer. So the minus 3 dB point on the y-axis, as indicated by the dotted green line on the graph on the right side of the slide, is the accepted threshold for a loss budget. This represents the point at which 50% of the signal level is lost on a connector. So the x-axis represents frequency. In this graph here, it shows from 10 megahertz up to 16 gigahertz. The measurement results are de-embedded to exclude the losses of the PCB traces, but the effects of the plated through holes are included in the measurement. So the worst case is differential 5, and this is due to the fact that there isn't a ground on the bottom of the differential pair. This creates an unbalanced differential line, which is why the performance is lower. The signal layout is dictated by Beta in order to conform to their specification. So all BPX connectors that are designed to Beta will suffer that same fate on that differential 5 line. So once you have the frequency content, you can calculate the data rate that the connector will perform to. In this instance, the frequency doesn't cross the minus 3 dB threshold to about 8 gigahertz. This equates to data rate. So when I talk about data rate, I'm talking about digital signals at about 16 gigabits per second. Excuse me. Another important consideration is return loss. The minus 10 dB point indicated on the right, the green dotted line, is important because it represents the point where 30% of the signal is reflected back to the source. This loss is due mainly to impedance discontinuities in the interconnect. Every time the signal sees a change in impedance, part of the signal moves forward and part is reflected back to the source. So if you recall from the previous slide, we benchmarked the insertion loss at the minus 3 dB point, or 50% of the transmitted signal. So where did the other 20% go? So those losses are due to both conductor and dielectric losses that occur within the connector. So that's the reason for the difference in the power levels from insertion loss to return loss. So it's important that your connector system is optimized to minimize the amount of return loss for optimal transmission of the signal. So in this case, the minus 10 dB point is greater than 8 gigahertz, which enables us to achieve data rates up to 16 gigabits per second. So in the previous slides, we talked mostly about RF performance. So the eye diagram shown here is it's a visual measure of the digital performance of an interconnect. In the digital world, we deal with bits, call it ones and zeros, or you can also think of it as 1 volt, 0 volts. An eye diagram essentially overlays the ones and zeros in the time domain represented by the x-axis. The y-axis represents voltage. So in this case, 1 volt and 0 volts. The ones and zeros are overlaid millions of times, creating this graph. The center is considered the eye, and so as long as there's white space in the center, it's considered to be acceptable performance. In this case, this graph represents a data rate of 16 gigabits per second. So the eye diagram, in this case, is simulated using S parameters. So the previous slides, we took the S parameters from those, and then we ran them through a SPICE simulation to achieve a data rate of 16 gigabits when passed. So this is without any signal condition to amplify the gain in order to achieve the performance. So now we're going to take a quick break for a poll question, so I'm going to hand it back over to Katie. Thank you.
All right, Kevin, thank you so much. So right now, everybody, we do have a polling question for you. So I popped that up onto the screen. If you could give us your response, that would be fabulous. The question is, what types of space constellations are most common in your designs? Then we have a multiple choice answer here. So choose the one that best fits. We have low Earth orbit, or LEO. We have medium Earth orbit, or MEO. We have geostationary Earth orbit, or GEO. We have all of the above, or none of these. So I'm going to leave this up on the screen for you. If everybody could put your answer in, that would be greatly appreciated. Your feedback is always important to us. So I'm just going to read the question out again. What types of space constellations are most common in your designs? So go ahead and choose your answer. I'm going to leave it up on the screen for about 10 more seconds. All right, everybody, thank you so much for your answers. One more time, what types of space constellations are most common in your designs? All right, thank you, everybody that has submitted answers. I am going to move us to our results slide, and then Kyle, if you want to talk about our results, I'm going to pass it right over to you.
Thanks, Kate. Yeah, so looking at the results, it's interesting. It seems there's a lot of space customers on the call today. Majority are lower orbit LEO, so short life cycles, but also all of the above. So I'm assuming a lot of people here probably fit in that category as well in all of the above. And none of these, some people just maybe here today to interested in space and interested in the space product. So since a lot of people from the space industry are on the call today, there should be a lot of interest in this next section. So in this section, we're going to review the technical specification of EEE INST 002. To answer what EEE INST 002 is, we must understand its purpose. This is a technical specification written by the NASA Goddard Space Flight Center. The purpose of instructing designers and component vendors of baseline criteria for selection, screening, qualification, derating of electrical, electronic, and electromagnetic parts, hence the EEE designation, for use in NASA Goddard Space Flight Center space flight programs. So this document provides instructions for meeting 3 reliability levels of part requirements based on mission needs. Of these levels of part reliability, confidence decreases by reliability level. So the level 1 being the highest reliability and level 3 being the lowest. So level 1 parts are sometimes called grade 1 synonymously. They shall be selected and processed to level 4 missions requiring the highest reliability and lowest level of risk. A typical mission duration for this is, for level 1 programs, is 5 years or more. So level 2 should be selected and processed this level for missions with a low to moderate risk. So this balances the cost and with mission objectives. The typical mission duration for level 2 programs varies 1 to 5 years. And level 3 are parts that are identified for mission applications that are used where the use of high-risk parts is acceptable. So the typical mission duration for level 3 programs is 1 to 2 years, less than 1. So section C2 in this specification is titled Connectors and Contacts, and it outlines the various connector and contact requirements. So for the purpose of today's presentation, we're going to concentrate on the requirements for printed circuit board connectors for PCBs. So table 3D, which I've duplicated here, outlines the qualification requirements for printed circuit connectors. First, visual and mechanical inspection performing workmanship and dimensional inspection is pretty generic and, the first step in most times when we talk qualification. Then dielectric standing voltage. So I'll summarize each one of these and kind of how or what is done. Obviously, the test methods and conditions requirements are more detailed. You can look those up in your own time. The dielectric withstanding voltage you test all contacts applying a voltage for 60 seconds between the closest contacts. For isolation resistance, you display a constant 500 voltage from pin to pin and pin to hardware of the plug. The measurement should not exceed 5,000 megohms. For temperature cycling, this requires 5 cycles of rated connector exchange. There shall be no damage detrimental to the operation of the connector. So for vibration, the connectors are wired and made in a series circuit, which is typical in these types of tests, with 100 milliamps of current flow applied monitoring for discontinuities greater than 1 microsecond during vibration, which equates to about 15 G peak. The shock levels equate to about 100 G peak. And again, the test configuration is similar to the vibration setup monitoring for damage. For contact engagement, a test pin is inserted and the max engagement force shall be 4 ounces and the minimum separation force should be a half ounce for low insertion force contacts. And mating and non-mating force. For low insertion force contacts, the max mating force shall be 0.25 times the number of contacts, and withdrawal force should be 0.04 times the number of contacts. Low signal level of contact resistance, finally, is a voltage no greater than 20 millivolts between contacts, with the current limited to no greater than 100 milliamps. A contact resistance measurement should be no greater than 33.4 milliohms. So it's important to note that the specification requires that the qualification data must be less than 2 years old relative to the lot date code for flight parts. So also, as part of the qualification is a review of materials and outgassing. So this specification gives some guidance to preferred materials such as liquid crystal polymer, LCP, as a preferred dielectric material. Non-metallic materials used in connectors should also be non-combustible and self-extinguishing. As part of the qualification, again, for printed circuit connectors, the evaluation of these outgassing properties is required. So non-metallic materials shall not exceed 1% total mass loss, or TML, or 0.1% collective volatile condensable material, CVCM, when tested in accordance to ASTM E595. So essential materials can be selected from the NASA reference publication 1124, which is essentially a database of outgassing data for spacecraft materials, or MAPTIS Materials and Process Technical Information Service. And if those aren't available, testing should be performed for ASTM E595 for materials that do not have these traceable references. So IEEE INS-T 002 also defines production screening. So in section C2, table 2D, outlines the screening requirements for printed circuit connectors. Both visual and low signal contact resistance is performed at 100%. And for mechanical, dielectric withstanding voltage, insulation resistance, contact engagement and separation force, and mating and unmating force, there's 2 parts per lot are sampled for inspection. So KVPX for space. So now we'll discover the benefits and features of our KVPX for space product and how it aligns to EEE IST 002 specifications. We now offer our KVPX connector series qualified and screened to the spec level to level 1 requirements, ensuring optimal performance in the challenging environment of space. So, as we discussed earlier, level 1 parts are selected and processed to this level for missions requiring the highest reliability and lowest level of risk. We're able to leverage our hyperbolic contact technology, which has been already proven in space in our NASA or in NASA's S311P 822 qualified compact PCI series, to expand our space qualified cost product offering into the KVPX series. In doing so, no sacrifice has been made to any of the electrical performance. So earlier in the presentation, Kevin presented some details on the different connector configurations offered in our standard KVPX series. We've now built onto that standard offering and newly offer a space qualified version for each connector configuration. As you'll see in the product brochure available here to download and on our website, we have included a -SL1 suffix to all standard KVPX connector configurations to include the EEE IST 002 level 1 qualification and screen. When the parts are built, they are screened and data packs are included with the part shipments. The qualification data, again, must be less than 2 years old relative to the live date code for these parts. So we briefly mentioned outgassing in the earlier slides. This is how it applies to our KVPX series. We discussed earlier that the requirements for space to review materials for outgassing for non-metallic materials should not exceed 1% TML or 0.1 CVCM. So in our space qualified KVPX, we use molded LCP dielectric to retain our electrical contacts. LCP is listed as one of the preferred materials, as we discussed earlier. And NASA reference publication 1124, which is the database for space materials, lists the material as having 0.06 TML and 0.01 CVCM. Our end modules include an additional end shield to provide additional electrical isolation at the end of a series of side-by-side daughter card connectors. This end shield is epoxied on with NASA-approved epoxy that has been independently tested to ASTM E595 for outgassing and is included in publication 1124. So this has, as you can see on the screen on the table, 0.77% TML and 0.04 CVCM. So now let's review how the new levels of qualification for the space testing aligns with historic VPX standards and our legacy KVPX specification. So in our recent presentation on threading corrosion and ruggedized backplane connectors, we did a deeper dive into these VPX specifications. However, by reviewing the table, you can see how our KVPX series standard has always exceeded the highest level outlines in these specifications. So as you can see, our recent space qualification has taken that another step further and closer to preliminary objectives of next generational VPX requirements, which are on the far right, which are currently being discussed in VITA 85106, which is called the VPX Expanded Study Group. So following our recent space qualification, we are incorporating a higher level of vibration and mechanical shock into the specification of our complete KVPX series of connectors. On the previous slide, you can see the comparison between what these original values and the new qualification levels were. Our hope is these improvements to our product specifications will allow customers to continuously design to the more challenging requirements set by future space and defense programs. It's so important to note again that the addition of these higher specification levels, there has been no derating of the remaining specifications of the connector. So now back to Katie for any questions.
All right, gentlemen, thank you both so much for that presentation. So we are going to move into taking some questions from our audience members at this time. All right, gentlemen, so let's go to our first question here today. Kevin, I think you could probably take this one. This person is asking, when does Smiths plan to launch their space-qualified version of KVPX?
That's a good question. So actually, it's available for sale now. The literature has just recently been updated. So you can find our KVPX brochure on our Smiths Interconnect website, along with our application guide. So it's important to note that, the physical difference between the new KVPX and the KVPX that's screened, there is no physical difference between the connectors. It's really just the additional screening that we're offering.
Okay. Our next question here. All right, and Kyle, I think maybe I can give this one to you. Can you configure the KVPX wafers into different configurations?
Yeah, I think I can answer that one. So currently, only our standard configurations of wafers are available to order. These configurations align with most of our standard VPX architecture pinouts, as Kevin presented, and the other popular customer use cases like the full power modules. If we do not currently offer a configuration and the opportunity makes sense, then we would be happy to discuss possibly building a new configuration of our KVPX series. So it's something that you just reach out to us if that's necessary. Maybe there's an alternative solution that we can direct you to, or if it makes sense, it's something we may be interested in doing.
All right. Thank you so much, Kyle. All right. And our next question here, Kevin, I'm going to pass back over to you for this one. Are these connectors already used in space? What is the space use heritage?
Yeah. So up until recent years, press fit technology, before compact PCI was launched, was not really embraced by the space group. But as of this last year, we've actually designed it into two major space programs, one for manned flight and the other for just for non-manned flight. I can't really, divulge the customers in that case, but they are for two major customers, one in the U.S. and then one in Europe.
All right. Thank you so much for that answer. All right, Kyle, I'm going to go back over to you for this one. Do you have any design guidelines for KVPX?
Okay. Yeah. Yes. So as Kevin actually mentioned on that first question, we just updated our KVPX application guide. So that's available to download on our website. If you navigate to our KVPX product page and you scroll down, sometimes it can seem to be hidden, but there's a tab that says application notes. Once you click on that tab, there is the content for our application guide, which would help you in your designs.
All right, great. Thank you so much for that answer. Another one here for you, Kyle. Are there any plans to design a ruggedized backplane solution that can reach higher speeds?
Yeah, I would say as an interconnect company, we're always desiring higher density, higher speeds. So it's the goal. We're currently doing R&D on a higher speed solution. However, it may be 1 to 2 years before anything comes to market. So there are working groups out there that are currently working on higher speed solutions, but they've yet to prove we can meet environmental requirements for space, which is something we'd be interested in. So as we work on that, hopefully in the next 1 to 2 years, we can come out and talk about a new solution.
Okay, great. Thank you so much for that answer. All right, so Kevin, I think this is kind of a follow-up or the same person asking this question from the one we answered prior. Are these solderable or flush mounted?
So it is a solderless connector. So it uses a compliant eye technology. So if you look at our application guide, it specifies the via hole size that the connector needs to be designed to, and the connectors are actually pressed onto the boards side by side. So they're not solder. They're not a solder connector. Not quite sure what flush mounted means, but you know they mount flush with the board if that's what the intent of that part of it is.
All right, thank you so much for that answer. So just a reminder to our attendees that we have some items in our resource widget. One of those items is a PDF of the PowerPoint from today's presentation. So if you're looking to grab anything from that resource widget, you can download those items at any time while we're doing our Q&A session. So feel free to grab those items right now. We also have a survey listed below. If you would like to fill out the survey, your feedback is always important to us. All right, gentlemen, we have a couple more questions in our queue here. So I think we've got time to take about one more. So Kevin, I think we can go to you for this one. Has the KVPX been qualified to any other standards other than EEE IST 002?
Okay, yeah, and so the answer is yes. So it's the typical qualification for KVPX before we did the space qualification was MIL BTL 55302, and then we've done application-specific vibration and shock. I can't really disclose the levels for those particular applications, but we have done in bespoke applications. We have the capability of taking it to higher levels and even using sawtooth and SRS shock. So, but yeah, the standard qualification for KVPX, the product line itself is 10 years mature, used a lot in defense applications where ruggedized connectors are needed. So a lot of times customers will come to us with specific vibration and shock profiles, and we'll test the connectors to those profiles. At a charge, I should mention.
All right. Thank you so much, Kevin, for that answer. So as I mentioned, if you don't have hear your question being answered, do not worry. We will reach out to you following today's webinar. And those are all the questions that we are going to take at this time. So anybody, if you have another question or think of another question or comment following today's webinar, you can come back and ask that question at any time. So feel free to do that if you think of anything following today. So right now, gentlemen, I am going to wrap the webinar up. I want to say a huge thank you to Kevin and Kyle for giving such great information during our presentation and for answering some of our attendees' questions. So gentlemen, thank you both.
All right. Thank you all.
Thank you, Kate.
Thank you, Katie.
All right. Thank you guys so much. And a huge thank you to our audience as well. Take care, and we will speak with you soon.